All right, what's good, everyone? So what we're gonna talk about in this video is an introduction to this extra sum of squares f-test, which we're gonna call this overall f-test that'll honestly become a little bit more important in multiple regression, but we might as well introduce it in simple linear regression when we kind of have some good visuals and things are a little bit simpler with just one predictor in our model. And so we're gonna end up applying this to this golf example that we had been working on with the t-test hypothesis test that we did. And the hypotheses for this test are actually going to be exactly the same. And this is only really the case in simple linear regression. So if we add more predictors, then the hypotheses for these two tests, the t-test that we did before and the f-test that we're doing now, are going to differentiate. But for now, they're the same exact test. So the model under the null hypothesis is still just the constant mean model, and so there aren't any predictors in this null model where y is the driving distance. And the model under the alternative hypothesis, where beta 1 is not equal to 0, is our simple linear regression model that we've been working with throughout this section, where x is our driving accuracy. All right, so there's a few things that we need to kind of define a bit before we jump into the components of the test. And the first set of things that we're going to define are these degrees of freedom. And so we're going to define them first and then give some kind of intuitive reasoning for why these degrees of freedom are defined this way. And so our degrees of freedom for total are going to be n minus 1. For the model, they're going to be p minus 1, which in the case of simple linear regression is 2 minus 1 because p is the number of betas or parameters in our model. And so this is in our full model, really, so the alternative hypothesis model. And the degrees of freedom for error are n minus p, which again, in the case of simple linear regression, is always going to be n minus 2 because there's always just one predictor, and so that means there's two parameters. There's a beta naught and a beta 1. Okay, so the reason for these degrees of freedom will provide a kind of lazy-ish reason, because again, this is applied regression, and so we're really tending to focus on the application and less on the theory, but we don't just want to like throw these out here without any explanation at all at the same time, so this is kind of the compromise we're making. And if you remember, the sum of squares total, we're adding up the observed response values minus the mean, squaring each of those and then adding them up. And there's going to be n observed responses, and so they're kind of, you could think about them as n independent pieces of information. Whereas the second part of this, there's only going to be one sample mean. And so this kind of has to do with y in particular, the degrees of freedom for the total are n minus 1. The same logic would hold for, we'll do SS error, where you add up the observed minus the fitted, because the fitted has these two parameters in there, then there's still going to be n distinct response values, but to get the fitted values, you only need two different parameter estimates. So you only need the beta hat naught and the beta hat 1, And so you just need two things to get those fitted values, really. Again, this explanation is kind of hand-wavy, but as mentioned before, this is meant to be applied regression, not regression theory. And so we're just going to kind of leave it as that, or leave it at that. These degrees of freedom are used to get these mean squares, which we'll end up using to construct our F statistic. And so the mean square for the model is defined as your sum of squares model divided by your degrees of freedom for the model. And so you'd find the sum of squares model by hand if you really wanted to do this by hand, and then divide by, in this case, 1. So in the case of simple linear regression, the mean square model is actually the same as the sum of squares model. Mean square error is the sum of squared error divided by the degrees of freedom for error. And so, again, you would find sum of squared error through this formula if you wanted to do it by hand, which we usually won't, and then divide by your sample size minus 2, which are the degrees of freedom for error. One last little piece of information is that if you go back and look at the definition for sigma hat with sub epsilon, so the residual standard error, it's actually the square root of the mean squared error. Okay. Mean square total isn't defined because it doesn't get used, and we only really define mean square model and mean squared error because they end up getting used for this F test. And so the F stat for this ANOVA F test is the mean square model divided by the mean squared error. Just like the T distribution, which had degrees of freedom, the F distribution also has degrees of freedom, and for this distribution, there's actually 2 different degrees of freedom that would define its shape, center, and spread. For simple linear regression, the numerator degrees of freedom are the degrees of freedom for model. And for simple linear regression, we already said that that's going to be 1. The denominator degrees of freedom is the degrees of freedom for error, since that part appears in the denominator of the F stat equation. And we already said that that's going to be n minus 2. And so these are going to control the shape of this F distribution. And so if you go to StatKey, so you don't really have to do this necessarily, but if you went to StatKey and looked at that F distribution and plugged in 1 for the degrees of freedom for the numerator, and we'll use our golf example, so the denominator degrees of freedom would be 193. You'll see that the shape of the F distribution is very right skewed. And so it's always going to be right skewed to a certain degree. And how right skewed it's going to be, as well as where its center is at, is going to be determined by these degrees of freedom. We'll pick up here in the next video with this last little bit. And so far we've really just talked about the kind of the theory of this F test. We'll pick up in the next video talking a little bit more about the application and see if we could kind of reason through what this, I guess the size of this F stat and what that would mean for our hypothesis test for an association.